Hi, welcome to Beat Physics. In this video we're going to be covering the essential skills necessary to do well in the AP Physics 1 exam. Over the past 18 years I've taught a lot of different physics courses, and it turns out you need to master a lot of skills in order to really understand the content and to be a great problem solver. Now it turns out that the College Board has released 10 specific essential skills, and what we're going to do is review each of these 10 skills, talk about some important details, and do some examples. For our first 3 skills, it's going to be focused on drawing diagrams, charts, qualitative sketches, and quantitative graphs as well. Now, for each of these 3 skills, they're not necessarily something that you will just do a ton of reps of before an exam. They're different skills that you would develop throughout the school year, doing different labs, activities, practice tests, etc. But you want to make sure you for sure have these skills down. So when it says create diagrams, tables, charts, schematics, and things like that, they're really talking about, are you able to read a situation, look at a diagram, and be able to develop some kind of diagram based on the stuff that they're showing you. Maybe something like a free body diagram. You might have stuff like bar graphs. You might draw some vectors on some different diagrams, etc. Okay, obviously there's a lot of variation there. It really depends on the type of situation. They could ask you for any kind of physical representation or graphic of what they're explaining or showing to you. Secondly, it says create qualitative sketches of graphs that represent features of a model or the behavior of a physical system. Now this one typically can be a little bit on the tricky side because sometimes people like to have a set of numbers to plug in, so when you have to work it out conceptually, sometimes it could be a bit difficult. For example, maybe you'll have some kind of displacement graph where it's a position versus time graph and you have a spring oscillating back and forth, and you'll just have to draw some kind of graph that goes like this that represents the situation. And you wouldn't necessarily have numerical values to plug in, but based on what they're describing to you with the positive and negative displacement of an oscillating system, you might have to sketch some kind of graph like that. That is, like I said, considered a qualitative sketch. Now lastly, we have a quantitative graph with appropriate scales, units, and plotting data. Obviously there's a lot more skills embedded in this one, so I'm going to break this one down a little bit more, which should hopefully mostly be review here. So it looks like we have time in our first column and distance for our second one. So time would be our independent variable, so it would belong on the x-axis. So we got time over here. We're going to include our unit of seconds. And distance appears to be our measured variable, which is our dependent variable. So it would belong right over here. So distance in meters. If I were to title it, I'm going to go dependent versus independent. So distance versus time. I'm going to go ahead and start my origin from 0, 0. And I want to make sure I know how to scale my graph. Now what I'm going to do is I'm going to take a look at my range of numbers and also take a look at the amount of space that's given to me on the graph. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so I got 10 spaces up, 10 spaces over. So let's go ahead and take a look at our times. So the times go from 0 to 5. So that's some pretty easy math. We can just go 1 second every other box, and that would hit all 10 boxes. So we'll go 1, 2, 3, 4, and then 5. Now, typically if AP is scoring your graphs, they just want a reasonable scale. So they don't want a graph that is really, really condensed in the small section, and they don't want a graph that's going off the chart as well. So I think as long as you have a reasonable scale that fits on the graph and covers, I would say, a decent majority of it, then you're pretty good with your scaling. For the distance, it goes to 20.1. So if we take 20.1, divide it by the 10 boxes we got. So obviously if we went by 2s, then we would fall a bit short, and then our numbers would go off of the graph, which we want to avoid. So anytime you do this little bit of math, you always want to round it up. So it's okay if we go over. So let's go ahead and go by threes. 3, 6, 9, 12, 15, 18, 21. And then we can go ahead and stop there because we know our numbers aren't going to go above 21. Okay, so let's go ahead and plot these points. We have 0, 0, 1 up to 3.9. We're going to sort of eyeball it the best we can. 2 up to 8. 3 to a little bit over 12. 4 to about 16. And then 5 to slightly over 20. I'm just going to go a little bit under this 21 over here. All right, so I'm going to do a reasonable job plotting my points. Obviously, if you're doing something by hand, it's not going to be perfect, so we just want these dots and data points to be reasonably placed. Second of all, after plotting these, you would want to be able to place a best fit line in between these points. These ones actually look pretty linear, but you may be asked to draw some kind of best fit line. In that case, you're going to take a straight edge of some sort and then try to line it up as best you can. I didn't take a straight edge there, but there you go. There's my best fit line. So for this one, there's a few more details that you want to make sure you're aware of. You want to make sure you label the independent with its units down here, the dependent with the units on the side, the dependent versus the independent. I'll just put DV versus the IV for our title. Obviously, be able to plot points in a chart and then maybe place a best fit line on there. Usually after that, you'll probably do some analysis with slope or finding area underneath the curve, but that's not necessarily part of what this skill is discussing at this point. All right, so that pretty much covers skills 1A, B, and C, which is basically being able to read and analyze a specific situation and then draw out different diagrams, be able to do quick sketches that are based on concepts like I did with 1C over here, and then with 1B, maybe be able to get into a little bit more detail with scaling and plotting data. All right, so let's go ahead and move on to our next section. Now for these particular ones, you do have specific questions that help you build up these different types of skills. Again, these should be things that you sort of develop throughout the year and hopefully aren't trying to cram and develop last minute, but if you are, then whatever, hopefully you'll develop them as much as you possibly can. All right, so for skill A, we have derivations. That is one of the big challenges in physics, is taking a bunch of concepts, mathematical stuff, and then not actually plugging in numbers and then doing a lot of algebraic operations and finding a final solution. So this first one says, which of the following is correct expression for the speed VA of the block at point A? So these questions are pulled straight from the AP booklet. And the answers are already bolded, but we're just going to kind of pretend at the moment that we don't see the correct answer and work our way through this. So we have a block that's sliding down a ramp across distance L, has a certain angle theta, and then hits point A. Now, what I'm thinking here is if we're taking a look at those kinds of things and we want to find a velocity, that we're going to be dealing with some stuff with forces and some kinematic stuff as well. Okay, this one, there's a bunch of different directions you could take it. You could maybe take a look at it in terms of looking at conservation of energy. Based on what I see here, I have velocity choices, and then I have g values, I have theta, and I have some mu values in there, okay, which would indicate to me that it looks like they're looking at it by using Newton's second law and taking a look at some forces. Okay, so I'm going to start with that route. So I have my FG, my FG going straight down as usual. We got our normal force up perpendicular from the surface, and then we have our force of friction opposing the slide as it's going down. And we have our perpendicular and parallel component. Okay, so if we're using Newton's second law, we are going to say that we have Fg, that is our force propelling it downwards. I'll call that my Fgx. It's just this parallel component right here. And then we have the force of friction opposing it, and that's going to be equal to m times a, as it usually is. So our Fgx is going to be mg, and then because it's the opposite of theta, mg sine theta. Okay, for our force of friction, it is mu k times the normal force. Okay, we don't have the normal force directly, but we know that it's equal and opposite to this y component over here. Okay, so this is going to be mg cosine theta. And that's going to equal m times a. So far, let's see, we can go ahead and drop the m's out, which is nice. And then from there, it looks like I have acceleration equal to a bunch of stuff over here. All right, now based on my answers here, as I said, there's a few different directions you can go, but they have a square root for each one of their answers. So if I'm taking a look at my equation sheet and I'm looking at kinematics and forces and things like that, the only thing I see with a squared value is the formula Vf squared equals the initial squared, V naught squared, or Vi, plus 2 times A times, we'll call this delta x, which is our xf minus our x naught, or xi. So that would be the only formula I can think of that we're going to eventually take the square root to find that final velocity. So that to me would make the most sense. In order to do that, let's see, we would need a Vi, which is 0, so we like that. We would need an A and a delta x. Our delta x we are good with because we call that L, and it does look like there's an L value over here. So we can go ahead and take this A and do a little substitution. So let's see if this all works out for us. So we have Vf squared equal to, and then we still have the 2. We have the coefficient of 2 in front of it as well, and we have the L. So we'll just call that 2L and put that together. And then this entire chunk over here is our A. So this will be G sine theta minus mu k G cosine theta. Okay, and we can do a couple more things here. We have a G in both of these, so the G can be pulled out and then placed over here. And then we're going to square root both sides to find the velocity. All right, so let's see what we got over here that matches up. Okay, we're looking at this one. This is way too simple. This doesn't have all this stuff. I don't have anything inside my square root sign that's subtracted besides this one over here. It has something subtracted in it, so I'll see if this matches up. So square root of 2gl, so I have 2lg, so just same thing, different order. Sine of theta minus mu k cosine theta, so sine theta minus mu k cosine theta. Okay, so then obviously this one checks out, which is why it is our bolded solution. So you see what I did there? I had to take a bunch of different concepts, but also I had to take a look at the answer that they gave me and sort of work with it. So I used a few different clues. I saw some angles and stuff over here, which would make me think of using forces in Newton's second law. And then I saw the square root symbol in each of the answers, which triggered me to look at this kinematic formula and pull that from my formula sheet as well. So using a combination of those, although it was a pretty difficult problem, there was some major clues there. And of course I had to have some algebraic skills to move some stuff around, cancel some stuff, pull some stuff out in order to get a solution that matched up. All right. Now taking a look at 2b, so these are calculations, these are just plugging numbers in, so obviously doing something similar to what we did with skill 2a, but actually plugging in some number values. So if I go ahead and plug in some number values, the thing is you have to be very careful placing stuff into your calculator, using parentheses, and then making sure things don't get combined in the incorrect way just because your calculator isn't quite understanding what you're doing. Now, if you're a little bit nervous about that, I would say do more separate steps as opposed to just putting this whole entire chunk all at once. So what I would do is I'm going to go ahead and put in 2. And then for g, we're going to use the rounded value of 10 times L, which they told us is 1 right over here. So this whole chunk is just 20. Okay, and then we're going to multiply that by sine theta sine of 30 minus this whole chunk of mu k cosine theta. So mu times cosine of 30. All right, so in my calculator, I'm going to do sine of 30 minus the product of 0.1 times cosine of 30, and then I'm going to multiply that by 20. And then that's going to give me 8.26795. And that's after I multiply it by this 20 on the outside as well. And then let's go ahead and square root that number to finish off. And then that gives us 2.875. Okay, so we got 2.9 over here, which is obviously, if you round it to one number after the decimal, that matches up with that answer. Okay, so again, when you place stuff in your calculator, number one, you probably want to write things down and not just place them directly into your calculator. And then number two, you may want to do some calculations in separate little chunks. For me personally, I did sine of 30 minus the product of these two, got that number, and then hit times 20, got this answer, which is the solution before it's square rooted, and then I've square rooted that number to get my final solution of 2.875, rounded off to 2.9. All right, let's move on to the next one and finish off our skill 2C. All right, so here's our skill 2C, and then, 2D as well. I forgot there's a D for this one. We still have a block that's released from rest near the top of a rough ramp, inclined at angle theta, and that basically just re-explains the situation we were in before, which is basically a block sliding down a ramp, experiencing friction, and then hitting point A eventually. So in this particular case, we have to compare physical quantities between two or more scenarios or at different times and or locations within a single scenario. I would say this is a pretty common kind of question where we have to analyze something and then reanalyze it with some different parameters. So it says the work done by the force of gravity on the block as the block slides from the point of release to point A is W1. Okay, so I'm going to do a little bit of drawing here. So work done by gravity, that one is called W1. The angle of the ramp is increased, and the work done by the force of gravity on the block as the block slides from the point of release to point A is W2. Okay, so this one is tilted up, greater angle, and then we still have some sort of work done. That one is W2. All right, so how does W1 compare to W2? So the work that's being done by gravity is that force which we talked about before once we make our triangle, which was mg times the sine of theta. That's the component of gravity that was pulling the block down the ramp. And then times that displacement, which we called L, or which they called L, which now we call L. And going from the first situation to the second one, this theta over here is increasing. So if that theta increases for W2, that would mean that the work would have to increase as well. So that would mean it's this one over here. W2 is going to be greater than W1. And if you're freakish like me, and although I know if I increase the theta, that number is also going to increase, I'm still going to put maybe sine of 30 in my calculator. Whoops. And then get 0.5, and then maybe put sine of 45 in my calculator, and then get 0.707. And I already knew that was 1/2 and square root of 2 over 2 for both of those. But like I said, if you're kind of in the middle of a test and you're kind of stressed or blanking, you can always use your calculator to do a quick little check like that. and then confirm that your idea is correct. All right, so let's go ahead and take a look at this last one. We have the energy dissipated by the frictional force as the block travels from the point of release to point A is called E1. And then if the coefficient of friction between the block and the ramp is doubled, the energy dissipated by the frictional force as the block travels from the point of release to point A is E2. All right, so this is actually something we sort of looked at earlier as well, which is taking the normal force, or the coefficient of friction times the normal force. So we got mu k times, and then we used mg cosine theta for our Fn. Okay, in the second case, the coefficient of friction is doubled. So this value goes to double the amount, okay, from E1 to E2. Okay, which would mean that E1 is a single value of energy, and then the next one, the mu k, is doubled, so the second one would have to be double as well. Okay, this one, it says the bolded answer is 2. I believe the answer is 1/2, and I checked with a couple of other physics teachers as well, and they agree that it's 1/2. So maybe there's something I'm missing in the question there, but it seemed to me that it was kind of obvious. If you double the coefficient of friction, then you have more force, therefore you have more energy dissipated, and your answer should be A. For the last 3 skills, we have 3A start over here on the bottom. We'll address 3B and 3C first. So for 3B, we're going to apply an appropriate law, definition, theoretical relationship, or model to make a claim. So it says, which of the following statements is correct about the total mechanical energy in the scenario above? So we still have our ramp and our block, and then in addition to that, we have the Earth involved in the system, or else we wouldn't have any gravitational potential energy. And then we had some friction going on caused by the ramp that causes some thermal energy. So let's go ahead and take a look at our choices and see what we got going on here. The total mechanical energy of the system consisting of only the block decreases from the time of release until the time when the block reaches point A at the bottom. Now, if we're looking at only the block, it has a velocity of 0 up top, and then finishes with some non-zero velocity at the bottom, which means that the kinetic energy definitely increases. So according to this, it says only the block decreases, so that is definitely not true. Now for B, the total mechanical energy of the system consisting of only the block remains constant from the time of release until the time when the block reaches point A. That is also not true for the reasons we talked about over here. Now we have the total mechanical energy of the system consisting of the block and Earth decreases from the time of release until the time when the block reaches point A. That one definitely sounds to be true because we have a certain system here, which includes the block and the Earth, and we know that overall it's losing energy because of the friction and thermal energy, and then some of that energy is leaving the system because it's going to the ramp itself. So that one definitely sounds correct. And then the last one says the total mechanical energy of the system consisting of only the block and the Earth remains constant from the time of release until the time when the block reaches point A. Okay, so it wouldn't stay constant because we're including friction. As I said, it is releasing energy out of the system into the actual ramp itself in the form of thermal energy. So C definitely does check out as the correct answer. All right, let's take a look at 3C. Which of the following statements correctly explains why the total mechanical energy of the block Earth system decreases as the block travels to point A? So as I mentioned earlier, it has to do with the force of friction and the gain in thermal energy based on that irregularity from the ramp and the block. So A, the height of the block above the surface of the Earth decreases. So the change in height doesn't really matter because that's mostly just getting converted into kinetic energy. B, the force of friction removes energy from the block Earth system. So that definitely sounds like it's true because, like we said, we have thermal energy going into the ramp because of that friction. And then the downward gravitational force exerted on the block by Earth does negative work on the block Earth system. So the gravitational force does actually increase the kinetic energy, so that would actually be positive work. And then D, the normal force from the incline, does negative work on the block Earth system. The normal force single-handedly does not do that. The normal force has to be combined with the coefficient of friction, and that would be the actual force of friction, not just the normal force itself. Okay, so although I felt pretty good about this answer once I reached it, you want to make sure you still continue reading the following choices just to make sure you didn't make any errors earlier in your judgment, and then confirm that your earlier answer was correct by canceling out the later ones that would maybe sound incorrect because of some false claims in the later answers. Lastly, create an experimental procedure that are appropriate for a given scientific question. So for the free response section, you're definitely going to see something like this. For sure, you want to be very careful about reading the procedures for all of the labs that you're conducting. So you don't want it to just be your lab partners reading through the procedures and you helping them out. You want to thoroughly read the procedures yourself to kind of get an idea of how a well-written lab is supposed to be constructed. That way you'll realize how to set up the equipment, how to mention how things must be at rest and released a certain way, or things of that nature. On top of reading the procedures, you want to make sure you have some experience actually writing procedures as well. So that's definitely not as common. So for sure, definitely reading the procedures very carefully for all the labs that you conduct. And then number two, obviously taking that action and producing procedures yourself is going to be the second step in really developing that skill as well. So that could be something that you review, taking a look at your old lab notebooks and old worksheets. So definitely would recommend those things.